third example is impulse function. And what is the impulse function? Well, pictorially, it can be shown to be like this. Oops, let me, as a f of t delta, let me draw a plan. So, let's see. So we're given function, and this only exists at the origin, let's say with a weight of 1 and 0. You can have other weights, and this weight, can think of this as the area underneath this impulse. Okay? What's a good model of an impulse function? Well, one is lightning. Another one is a bomb. Okay, because you have nothing, and then something, and then nothing back again. That's a very high frequency for a short amount of time. Another sparks. Okay, and these are the different models for bombs. So that gives you a physical feel what an impulse function does. And sometimes the response of a system can't respond that quickly given by this impulse. So usually that's let's say right here, and that's what happens that when it doesn't respond to that. Okay, so very thin, infinitely thin pulse to something that it's wider. Okay, which implies that there is some limited response to this high frequency impulse. All right, so what we want to do is show, okay, having a problem right here to get down. Okay, so we'll say this, erase all that ink, and then select the arrow. Okay, so our Laplace transform for this delta function is a constant. So anything that's thin in the time domain is very wide in the frequency domain. Now let's evaluate this function. And this function only exists when t equals 0. So we're going to use that property. It makes integrating very easy. So we'll apply this definition here, substitute the delta function in our definition of a Laplace transform. So just substitute here into here. And what we have finally is that this integral only exists when t is equal to 0. When t equals 0, that's just equal to 1. Okay, because when you substitute t equals 0 here, this reduces to 1, and then this whole integral has an area of 1. And that's because the impulse response, once again, only exists at t equals 0.